At this point, we know enough pic24 instructions to write a simple program. In this class, we will present all programs in C language form and then manually translate, that is, compile them to the pic24 assembly language. We do this because later in the semester, when we write complex programs, we will always write them in the C language and then use an automated compiler to produce pic24 assembly language. And what we want you to know is we want you to fully understand the linkage between what you write in C and what actually gets produced in pic24 assembly language. So let's get started. This is a very simple C program. We're first going to do a pound define construct that is going to essentially simply define a constant called a value, and we'll arbitrarily give it a value of 100. We're going to use three 8-bit variables, I, J, and K. This is going to be the type declaration that we're going to use for an 8-bit variable in the C language. This program is meaningless. It's simply going to do a sequence of operations. We're first going to copy the constant 100 into the variable location I. We're going to increment that variable I. We're going to copy I to J. We're then going to decrement J. And finally, we're going to add J plus I and place the result back in K. We have three variables in our program, I, J, and K. They're 8 bits wide, and we need to assign them the locations in data memory. Recall that the first free location in data memory for variables begins at location 800. Location 0 through 7FF is reserved for special function registers. So we'll simply assign I, J, and K to the first three locations in data memory, which is going to be 800, 801, and 802. We easily could have made other choices. So let's convert our C program to pic24 assembly. We're going to do this one C language statement at a time. So let's start with this one. These are all 8-bit wide variables, so we're going to use byte operations. We need to copy the constant value into I. You might want to say, okay, well, I'm going to do this. I'm going to say move.byte the immediate value 100 into location 0800. Unfortunately, there's no such instruction in the pic24 instruction set. We have to actually use two instructions to do this. We'll move the literal value 100 into W0. Then we're going to do a move.byte of WREG into location 800. Now let's increment I. To increment I, we'll use this form in which we'll say increment.byte memory location 800. Recall that this form of the instruction is going to take 800, add 1 to it, and then write the result back in data memory location. Let's copy I to J. We're going to move.byte the contents of location 800 to WREG, which happens to be W0, and then we're going to go ahead and copy WREG to location 801. You might have been tempted to write, I'm just simply going to write move.byte location 800 to location 801. Unfortunately, there's no such instruction. We have to do this with two instructions. Let's decrement J. We can simply use decrement.byte location 801. Remember that 801 refers to J, so that will decrement that location by 1. Finally, we're going to add the contents of J plus I and place the result into memory location K. This is going to take a 3 instruction sequence to do it. We'll first move location 800, which is I, into our WREG, which is W0. Then we're going to do add.byte the contents of location 801, which is J, plus WREG, which contains the value of I as moved by the previous instruction. That result will go into WREG. And finally, we're going to move that byte WREG into location 802, which is assigned to K. Now that we've converted our C language program to pic24 assembly language, the next step would be to take the pic24 assembly language and convert it to pic24 machine code. We could do this manually by determining the instruction format for each instruction by looking them up in the data sheet. This would be very tedious and time consuming, so instead what we're going to do in this class is we're going to use a program called an assembler to do this step for us automatically. That program is called the MPLAB Integrated Design Environment, IDE for short, and we're going to use that to assemble and simulate all of our pic24 programs. This slide shows the contents of a text file that has our program written in a format that's compatible with the MPLAB assembler. There's a separate video that fully discusses all the details of the MPLAB IDE and this use of this text file. I would urge that you view that video. I'm only going to hit a few highlights. These three statements right here declare a label for each of our variables. A label is starts in column 1 and it ends with a semicolon. And what we're going to do is we're going to reserve 1 byte for each of these variables. This dot space is an instruction to the assembler. It's not a pic24 instruction, and it says reserve 1 byte for this variable. Variables are going to start at location 800. So this variable I is going to live at 800, and the label I is going to stand for 800. J is going to be at 801, and K is going to be at 802. These three instructions here do some processor initialization. We'll talk about these later. Here is our program. The semicolon I equal 100 is a comment. These next two instructions is going to implement this operation. We're going to move the immediate value A value to W0. We're then going to move dot byte WREG to I. Notice that in this file, we're using the label I instead of using the memory location 800. That makes this much more readable. The assembler knows that I stands for location 800, so when it assembles this program, it will replace I with 800. This next statement here is going to implement the increment operation of I is equal to I plus 1. These two statements here is going to accomplish copying I to J. We first copy I to WREG and then copy WREG to J. This statement right here is going to decrement the contents of memory location J. And finally, these three instructions right here is going to implement J plus I and write the result to K. This statement right here forms an infinite loop in which we're going to say go to done. Well, done is the label for the start of this instruction. This is necessary during simulation of this program to catch the execution of this program at this point, so we don't execute any statements that follow this program. Let's take a look at another solution to this problem. There are generally many ways to convert a C language program into a semi-language. The previous approach examined each C language statement one at a time. Here we're going to consider the whole program. What we're going to do is we're first going to assign variables to registers. We're going to move these variables into registers if needed. We're then going to use register-to-register operations for the computations, and then we're going to write the variables back to memory. So let's assign I to W1, J to W2, and K to W3. These are arbitrary assignments. We're first going to do a move of the immediate value 100 in a W1. This is a word operation, but we don't really care what the most significant byte of W1 is. All we want is for W1 to contain the value 100. We then need to increment I, so we're going to increment W1 and place the result back in W1. We then need to copy I to J. So we're going to copy W1 to W2. Recall that we've assigned J to W2. We then need to decrement J. So J is in W2, so we're going to decrement W2, write the result back to W2. And finally, we're going to do this addition, so we'll use the 3-operand addition. We're going to add W1 to W2 and stick the result in W3, so that's adding I plus J and placing the result in K. At this point, we now need to write these register values to memory. Because these are bytes, we're first going to have to copy these registers to W0 and then use move WREG to whatever memory location that we're trying to write. So we'll first write out I, so we'll move W1 to W0, copy WREG to I. We'll then do the same for J, and then we'll do the same for K. At this point, the memory locations I, J, and K contain the values that they did with our previous approach. The previous approach only took 9 instructions, while this one took 11. As mentioned previously, we will never grade you for efficiency of your assembly language. Simply use whatever approach that you best understand. What if we wanted to use 16-bit variables instead of 8-bit variables? We would have to change this data type from uint 8 to uint 16. That would mean that each of these variables would occupy 2 bytes of memory. We're also going to change this constant value to something that requires 16 bits, something that is greater than 255, and so we've arbitrarily chosen the value 2047. The rest of the C language program does not change. In our MPLAB compatible assembly file, we're now going to need to reserve 2 bytes of space for I, 2 bytes for J, and 2 bytes for K. That means that I will reside at location 800, J will reside at location 802, and K will reside at location 804. The rest of this program, all we've done is simply remove the .byte from the instructions. Other than that, this is the same program as for the byte program. What about our alternate solution that uses register-to-register operations? We've removed the .byte from these instructions, so now we're doing all of these are word operations. When we write variables back to memory, we now no longer have to copy the register in the WREG before we do the write. Since it's a word operation, we can simply directly write W1 to I, W2 to J, and W3 to K. This means that this approach is actually more efficient than the previous approach. This approach only takes 8 instructions. The astute reader will also note that we can actually save one instruction here. Instead of moving W1 to W2, which copies I to J, and then decrementing J, we can simply replace this with the following. We can say decrement W1 to W2. This is going to be equivalent of saying J is equal to I minus 1. This is something that an optimizing C compiler would actually do. Let's talk about how long a pic24 instruction takes to execute. The clock signal used by the pic24 microcontroller can either be generated off-chip by an oscillator or a crystal capacitor network, or by using an internal RC oscillator. For the pic24H family, this clock frequency has a maximum value of 80 megahertz. An instruction cycle, abbreviated as FCY, is 2 of these clock cycles, abbreviated as FOSC. Most pic24 instructions take only 1 instruction cycle. A few take 2 instruction cycles. If an instruction causes the program counter to change, such as a go-to instruction, then that instruction is going to take 2 instruction cycles. An add instruction takes only 1 instruction cycle. Let's determine how much time this is if the clock frequency FOSC is 80 megahertz. Let's review some units. 1 megahertz is 1 million hertz. Recall that 1 over the frequency is the clock period. So 1 over 80 megahertz happens to be a period of 12.5 nanoseconds, where 1 nanosecond is 1 billionth of a second. So 1 add instruction at 80 megahertz takes 2 clocks. So 2 clocks times a period of 12.5 nanoseconds means that this add instruction takes 25 nanoseconds. This is going to be the period of the instruction cycle. By comparison, a modern Intel CPU operates in the gigahertz region, which means that it operates orders of magnitude faster than a pic24. However, a modern Intel CPU also costs hundreds of dollars, while a pic24 CPU only costs a few dollars. If we look at our original implementation of our C program, the byte version of it, and include the instructions that initialize the processor, we find that this program takes 12 instruction cycles, which is 24 clock cycles. If we count the number of clock cycles for the Word version of our C program, we find that it also takes 12 instruction cycles. In general, a 16-bit processor does not gain any efficiency in operating on 8-bit data. Later on, we will discuss operating on 32-bit data, and we'll find that this will take approximately twice as long to execute than as on 16-bit data. Let's wrap up this lecture by having a discussion of units and unit conversions. In this class, units are always used for some physical quantity. For time, we'll use milliseconds and microseconds and nanoseconds. For frequency, we'll use kilohertz and megahertz and gigahertz. When a time, frequency, voltage, or current quantity is asked for, we will always ask for it in some units. Values for these quantities in data sheets are always given in units. So as an example problem, let's given a frequency of 1.25 kilohertz, what is this period in microseconds? So we're going to compute the period as 1 over the frequency. So it's going to be 1 divided by 1.25 times 10 to the third. By the way, this is shorthand for saying 10 to the third. If we calculate this, we're going to get a value of 8.0 times 10 to the minus 4 seconds. The problem asks for this in microseconds, so we got to convert seconds to microseconds. So to do a unit conversion, we'll take our seconds. We know that there's 1 times 10 to the 6 microseconds in 1 second. Here, seconds will cancel out. We'll do this multiplication, and we'll end up getting 8.0 times 10 to 2 microseconds. Multiply that out, we'll end up getting 800 microseconds as our final result. So this concludes our lecture on Chapter 3 material. We discussed the basic pic24 architecture in terms of the program and data memory organization. We covered a few instructions as well as their various addressing modes. We expect you to be able to convert some simple C instruction sequences to pic24 assembly language. In the lab associated with this course, we're going to expect you to be able to simulate pic24 assembly language programs within the MPLAB IDE. And we also discussed the relationship between instruction cycles and machine cycles. In future chapters, we will expand our coverage of the pic24 instruction set. Hi, this lecture will concentrate on some of the problems at the end of Chapter 3. First, we'll start with problem 11. So given a 20 megahertz FOSC, how long does it take the instruction move W2 to W4 to execute in nanoseconds? First step will be to compute the clock period in nanoseconds. So we know that period is equal to 1 over clock frequency. So 1 divided by 20 megahertz is equal to 1 divided by 20 times 10 to the 6 is equal to 5 times 10 to the minus 8 seconds. We need to convert this to nanoseconds. We know that there's 1 billion nanoseconds, 1 times 10 to the 9th nanoseconds in 1 second. So multiplying this out, seconds will cancel out. We'll be left with nanoseconds. We get 5.0 times 10 to the 1st nanoseconds, which is going to be 50 nanoseconds. So a 20 megahertz clock has a period of 50 nanoseconds. The move instruction takes 2 clock cycles or 1 instruction cycle. So multiplying this out, 2 times the clock period is 2 times 50 nanoseconds, and we get the final answer of 100 nanoseconds. Problem 13 says to write a pic24 instruction sequence that accomplishes k is equal to I minus j minus 32, where I, j, and k are all 8-bit variables. The solution in the back of the book for this problem is incorrect. You can visit the errata page at the book website for yet a third solution to this problem. This solution is going to use a 2-operand form of the subtract operation. First of all, we're going to move j into wreg, so w0 is going to equal to j. Then we're going to use this subtract operation, where if you recall, it does the following. It says I minus wreg, and the result will be placed into wreg. So what does wreg contain? It contains j as by the previous instruction, so I minus j is going to end up going into w0. We're then going to store this partial result in the k, so k will first equal to I minus j. At this point, we need to complete this by subtracting 32 from k. So we're first going to move the immediate value 32 into w0, and then we're going to use this instruction, which says k minus wreg, with the result being placed into k. What does k currently contain? K currently contains this partial result I minus j, wreg contains the value 32 by this previous instruction. So the end result is that I minus j minus 32 is going to be written to the memory location k, completing the solution to this problem. Problem 15 asks, how many add instructions using this form of addressing, register direct addressing, 3 operand form, how many of these instructions are executed in 1 second, assuming a 25 megahertz clock frequency? First, we'll compute the clock period in seconds. So the period is equal to 1 over the clock frequency, so 1 divided by 25 megahertz is going to equal to 4 times 10 to the minus 8 seconds. So one of these add instructions takes 2 clock cycles, so 2 times 4 times 10 to the minus 8 is going to equal 8 times 10 to the minus 8 seconds. We can now take this time for one of these add instructions and divide that into 1 second. So 1 second divided by 8 times 10 to the minus 8 second is equal to the final result of 12,500,000 add instructions. This solution is going to use a 3 operand form of the subtract operation. We're going to use W0 to store I, W2 to store the constant value 32, W1 to store J, and W0 to also hold partial results for K as well as the final result of K. So to get started, we're going to move the immediate value 32 into W2, and we're going to leave it there for later use. We're then going to move J into wreg, so W0 is equal to J. Then we're going to move W0 to W1, so that W1 contains J as per this register assignment here. We're then going to move I into wreg, so W0 is equal to I, and now we can perform this subtraction using a 3 operand subtraction, which will say W0 minus W1, which is I minus J, and the result's going to go into W0. To complete this operation, we need to subtract 32 from this. We know that 32 is sitting in register W2, so we'll use this 3 operand subtraction. We'll say W0 minus W2, which is going to be subtracting 32 from I minus J, with the result going into W0. At this point, W0 has our final result of I minus J minus 32, so we need to write that to K. After this instruction is complete, K is going to have our final operation of I minus J minus 32.